Hi, good morning. While people are finishing their coffee and coming in, let me quickly introduce myself. My name is Jan van Eldik. I work at CERN since 1993. I'm trained as a physicist, but I've forgotten most of the stuff that I was doing back then. I've been, since about the year 2000, I've been working in IT department, so I really am an imposter. I'm going to be talking about CERN, I'm going to be talking about computing, and I'm not an expert in any of the two, but I'll see if I can bluff my way through. So I'm the guy standing between you and lunch. So I've got a slide deck of about 40 slides. I can talk about that till the cows come home. But what I'd like to do actually is talk about it for about 40 minutes. And then I'd actually like it if you guys could be asking some questions. I'm first and foremost an OpenStack operator. I run the team at CERN that actually manages the infrastructure there. So if there's anybody who wants to know details about that, that would be a very good topic for that. Now, Andreas tells me that maybe the Swedes in the audience are a bit, could be a bit shy to ask questions there, so I've got two proposals to actually make you come forward and ask those questions. One is CERN stickers. If you've got a question, ask it, you get a sticker. Ook, det är också mycket möjligt att du kan fråga, du kan prata med i svenska. För jag börjar öva min svenska lite. Så om ni, ni känns lite timid och vill fråga någonting, fråga på svenska. Okay? I know I've got a little bit of a Skånsk accent and I don't talk very fast, so I'll do it in English. All right, here we go. I'll be looking at my slides here, I'm afraid. I don't know my slide deck that well. We'll see. So, the CERN OpenStack Cloud. What we do at CERN is we actually provide the compute facilities for the LHC experiments and the other experiments as well. In the presentation I'll be focusing mainly on the LHC use case, but it's an organizational cloud that we're running. I'll be giving an introduction to CERN, what it is we do there, what this means for computing and how we do computing, why we ended up with the cloud, how we operate it. I'll say a few things about our cloud performance before I come to the end of the presentation. So, CERN first. So CERN is the European Organization for Nuclear Research. It's 62 years old, founded in 1954. And with Romania joining recently, we've got 22 European member states. In addition to that, there's plenty of countries with different statuses, observers, for example. So it is a world lab. We've got contributors from all over the world, and it's actually a pretty exciting place to work. There's about 2.5 people employed by CERN who are working on the site near Geneva or on the French side. But there's many more people working at CERN, about 10,000 people on site every day, out of about 12,500 collaborators. Because the way CERN is, of course, quite a famous lab, but in a way it facilitates research. So it's owned by the member states, and we just run the accelerator if you want. The experiments are done by the institutes from the member states, by the universities. So they would typically send people there on a temporary basis to do research. But it's quite a lot of people. There's also quite a lot of money, as you can see there. A small part of that budget goes into computing. So what we do at CERN, we try to answer fundamental questions about matter. We do high energy physics. We want to test the physics models by running rather large experiments. And this is something we've been doing through since the beginning of the organization. Now the LHC and its 4 experiments are our flagship research, but there's much more than that. We've got experiments on the International Space Station, for example. I will not touch on that at all. If you want to know more about that, we've got a wonderful website, home.cern, where you can find a lot of information about that. So to do that physics research, we are pushing the boundaries of technology. I'll give you a few examples of that. Very important for us is also that we train people. We get university students coming to CERN for a couple of years, and then they do their PhD thesis and go into the world as very strong engineers, and they will end up in many different places. And last but not least, we do science for peace. So one of the CERN was founded just after the Second World War, and one of the stated goals was really to bring nations together to make science, not war, shall we say. So our flagship program is called the Large Hadron Collider. On this slide you see a couple of rings, and the big ring is the LHC. It's 27 kilometers in circumference, and it's hosting hosting 4 major experiments. So if we quickly talk about this slide, you see it projected on the right-hand side. You see the Lake Geneva. You see the LHCb detector close to the Geneva airport. You see on the left-hand side, you see the Jura Mountains and actually the ski resort of the Mont Jura, which is a bit like Ore, I understand. The big ring is the LHC. The smaller ring near Atlas in the bottom is called the SPS. It's a pre-accelerator, if you like, and the very small one at the bottom is the proton synchrotron, where actually the protons that go into the LHC are started. The computer center is not so far from that from that proton synchrotron. So it's huge. It's underground, about 100 meters typically. We've got almost 10,000 magnets to control, to steer the beam, to focus the beam. 1,200 of them are superconducting. You see a picture of one of those monsters there. They're 14 meters long, they weigh 35 tons. They have an 8.3 Tesla magnetic field, which is about 200,000 times the strength of the Earth magnetic field. And there's an awful current running through it. It's superconducting, which means that it is operated at a very low temperature, minus 271 degrees centigrade, cooled with 120 tons of helium, and it's colder than outer space, as is claimed here. The point is that only at that temperatures can we operate the magnets in a superconducting regime, which means that there's no excuse me, no loss of electrical power due to resistance anymore. So it's good for our electricity bill. Inside the beams, we operate a very, very high vacuum, comparable to the vacuum of the moon. As you can see here, we actually have 2 beams. We've got proton beams going in both directions, and they only cross over in the 4 experimental areas. These beams are operated at a very high vacuum because we do not want our protons, our precious protons, to interact with beam gas and lose events. So it's technologically very advanced beast, this LHC. And then the detectors themselves. So you've seen in the previous picture, we've got 4 of them. 2 of them, Atlas and CMS, are probably the most well-known ones. They are general purpose detectors that are testing standard model properties. And it's at those detectors that the Higgs particle has been discovered a few years back. They're huge. You can compare them to cathedrals. Atlas, I think, weighs as much as the Eiffel Tower. There's 3,000 people working for that collaboration, and 2,600 for CMS. So that's not much smaller. On the pictures, I think you can see physicists somewhere, but you need good eyes for that. The other 2 experiments, ALICE and LHCb, they're less general purpose detectors. They are really optimized for specific types of research. ALICE is looking at a quark-gluon plasma, the state of matter just after the Big Bang. And LHCb is trying to study very subtle asymmetries in nature. And they're all very successful as they are. So an animation of how things work. You see, let's say this is the Atlas detector. You see 2 beams of particles coming from the left-hand side and the right-hand side. And as I mentioned, they are separated in beam pipes, but they are steered to collide in the heart of this detector. So what happens there is that when the protons collide, the new particles are created. These particles are unstable, they fly in different directions and they decay. And it's those decay patterns that we try to detect in these layered detector systems. The different layers denote different technologies. I won't go into any details, but the particles leave their tracks in these detectors. They're read out. Filtered, and sent to the computer center. Now the numbers you see on this slide, I must confess they're a bit stale. This was of our first run 1, which finished a few years ago. But this shows the general principle of an enormous data reduction from the events coming from the detectors to what is actually sent to the data center. And that looks roughly like this. Again, the numbers are a bit stale. This was run 1, but what you see here are these 4 experimental areas underground where data is being collected, filtered, and then sent to the CERN computer center where I work. And for our first run, we typically had data rates of about 5 gigabytes per second coming from the 4 experiments combined to the data center. So that's 1 DVD per second that we need to crunch. That was the first run. Things are only have been getting worse since then, I say. So what do we do with all that data? We do 3 things with them in the data center. First thing is we store it. It's written to disk and then copied to tape for posteriority, because the data analysis is not done live, it's done offline. The physicists study the detectors, they get a better understanding of how they respond to the particles. Of course, the theories are modified as well, so we get a better understanding of what we're actually seeing in those detectors, and this is an analysis that goes on for years. So this data is stored for that. The other thing is it's copied. It is sent to collaborating institutes on what we call the LHC computing grid. The third thing we do is actually we do analysis inside the computer center of that data as well. So this LHC computing grid is a tiered system that we put in place, well, in the last 10, 15 years, where, if you like, CERN is the tier 0 institute in the center, where the data is being recorded, reconstructed, and distributed to a layer of tier 1 institutes. I think there's about 12 or so of them worldwide. Some of those are distributed. There's one Nordic one with a part in Stockholm here as well. And then there's the outer ring of universities and institutes worldwide. It's about 200. The number fluctuates. I think it's about 300 universities these days, where data analysis is taking place as well. So it's big. And CERN is the center of that particular computing grid. Now, I was mentioning that our data rates will grow over time. So what you see here on the right-hand side are the predicted computing needs for the coming runs. We're currently in run 2, which started last year. And there will be 4 runs. So the LHC is expected to run to 2030, as the planning is right now. Now, our physicist colleagues, they can consume as much compute power as we can throw at them, but obviously we cannot pay for that, right? So we have agreements with them on how much compute infrastructure we can put in place, and we ask our funding agencies to actually pay for that. And our funding agencies are very generous, but they don't have bottomless pockets either. So as you can see, there is actually a limit to what we think we can afford in terms of computing. Which means that we need to optimize our usage of those resources as much as we can. And this meant that we actually had to rethink the way that we are doing computing for the LHC. Up to 5 years ago or so, we were running everything on physical machines. We were very often handing out machines to the individual experiments, which was not particularly efficient. The way that we were managing this park was with homegrown tools, which was not very efficient either. We will maybe get funding to buy more compute power, but we're not going to get funding to hire more staff. So we need a system that allows us actually to scale those computing resources, particularly their operations, while keeping the staff numbers flat. I worry about the staff numbers because I am actually responsible for the team that operates our cloud infrastructure. So in about 2012, we decided to redo the way that we do computing for the CERN experiments. And we started to think about putting a cloud into place. This was, of course, very early days for OpenStack, and we've been involved in OpenStack since those days. So the aim of the project was to basically virtualize everything we can virtualize. If somebody feels that he needs a physical machine, he has to have a very, very, very good reason. We are rooting out the server huggers as much as we can. And we are actually quite successful at that, to the frustration of some of our users. So we realized that actually it would be very beneficial for our users if we could offer them cloud endpoints, because this, of course, the experiments are not only running on the CERN infrastructure and on the grid. They were also getting grants from companies like Amazon and later Google to use their resources. And they realized, yeah, if somebody offers us a cloud endpoint, we can actually make use of those resources in a very easy way, which is good for us as well, because we can decouple the infrastructure part from the application part and the user part. So that was attractive for us as well. I'm not going to reread what Thierry said there, but we want to be able to scale our operations horizontally, as I explained to you. A very important feature of cloud computing for us as well. And then we wanted to do something a bit not very cloudy. We also wanted to use this infrastructure for server provisioning or server consolidation, classic virtualization, if you like. This thing that you would actually buy VMware installation for, we wanted to do with our cloud, because VMware costs money and OpenStack doesn't. I have to be very blunt on that. Huh? We want to put our money in computing hardware. We want to buy the cheapest we can, commodity hardware, and we'd rather not spend money on anything else. So if we have all that, let's see if we can build a virtualization infrastructure as well as a cloud infrastructure from it. You'll see how we've been doing with that. So now we are 4 years later, and at CERN we actually run a couple of OpenStack clouds. So we run a very big one in the data center. I'll be focusing on that one. But in addition to that, the experiments, they have their online farms, as I showed you before. And when there's no data taking, because the accelerator is down for maintenance or the winter shutdown is upon us, they actually convert those online farms into OpenStack clouds. And they do data processing there, or they generate Monte Carlo simulated events. So we have about 4 or 5 different clouds at CERN. And they're big. So for us, the cloud is not the cloud is a tool, right? We want to provide our computing to work on our mission, which is fundamental research. So we actually run the CERN IT cloud in two distinct data centers. One is an old building on the CERN premises, where the bulk of our servers are hosted. Another one is a data center in Budapest at 23 milliseconds latency, connected via dedicated links. We've got about 2,500 machines there since a couple of years, which is pretty exciting for us to operate because it's part of the CERN network, but it's very far away. Server huggers, they cannot go to Budapest to push the power button. We have to automate everything there. So it's been very interesting for us. Now, no surprise to you in the audience, we decided to go for OpenStack quite early on. And we've been, after 1 year of pre-production services, we've been operating OpenStack in production since July 2013. And since then, we've been upgrading. We just finished our upgrade to Liberty. And some the we are already at Mitaka. As you can see, we are a little bit late, but I must say with the deployment of our size, we want to be a little bit behind as well. We cannot afford to be bleeding edge. We'd like other people to find bugs, and then you see my point. Our team is relatively small. We've got 15 people. Half of those are service developers, and the other half have more of an operational role. So we do contribute as much as we can, but we'd like to be able to contribute more, actually. We're convenient to be a little bit behind. So how do we architect our cloud there? The main component that we're running is, of course, OpenStack Nova Compute, where virtual machines are being provisioned. Now you may know that actually if you want to scale up to the size that we have with some 7,000 compute nodes, you use something called Nova cells as building blocks to scale out. So we run about 40 different cells. many of those in Wigner, in the Budapest data center, the others at CERN. On top of that, we have a top cell which talks to all those child cells. This is the only clustered rabbit setup that we have there for some redundancy. The API servers that we're running are VMs themselves. So, like Monty, we eat our own dog food because actually the dog food tastes pretty good. Here, schematically, on the top you see these top cell controllers, and then you see two examples of child cells with the compute nodes underneath. The cells that we run vary in size. A typical cell has about 200 compute nodes in there. We have some older ones with about 1,000, and we've got some smaller ones with special hardware that are smaller. We make do. I'll tell you why in a second. So Nova cells, even though they are still labeled as experimental, are crucial for us because they allow us actually to grow. And grow we do. So at the moment we have about 7,000 hypervisors in production. Most of those are running CentOS 7. But we still have a few machines running CentOS 6, if you like. We also run quite some Hyper-V nodes. As I mentioned, we want to use our cloud also for server consolidation use cases. So a lot of the Windows infrastructure servers are actually virtual machines running in the OpenStack cloud. At the time we thought it'd be wise to actually run those Windows boxes on top of Hyper-V rather than on top of KVM. This has worked quite well for us. We've worked with the OpenStack teams to make sure that Hyper-V is a first-class hypervisor under OpenStack. But we've realized over time that actually running Windows under KVM also has its advantages. In particular, as I said, our team is relatively small and our Windows expertise is relatively limited. So it's more important for us to be able to focus on KVM Linux knowledge and worry less about Hyper-V. So we are migrating away from Hyper-V to KVM. We've got about 200,000 cores. And that is about twice the size we were a year ago. So for us, it's very important to be able to scale those operations. Excuse me. We spent a lot of time upgrading and adding. And now, this year, very exciting, we're also removing things. Quite some of our hardware is coming to end of life now. So getting rid of hypervisors that are running virtual machines is also quite an interesting exercise. The graph you see here is the number of virtual machines created and deleted every 30 minutes in our cloud. And as it says there, it basically means that every 10 seconds a machine gets created or deleted, which is pretty active. Now I have to say, we do a lot of testing on our production cloud. We use an OpenStack component called Rally to see if we can actually create and delete VMs. So most of the things you see there is actually us testing if our cloud is working. And our cloud is working. The gap you see in the middle was actually our testing that was going down. In addition to these OpenStack components, we run Ceph as the backend for our Cinder volumes, as well as for our glance images. So the Ceph instance at CERN is a very big one in itself. I recommend, if you're interested in that, to look for some presentations on that. CERN is also very big in the Ceph community, and it works very well for us, I must say. So how do we deploy OpenStack at CERN? We are a Red Hat shop, if you like. So our hypervisor infrastructure is based on CentOS 7 now, and we use the RDO distribution of OpenStack. So the packaging into RPMs of the various components to install OpenStack itself. We have an upstream first policy. So whenever we need to tailor something that is of interest to the community, we actually try to push this upstream. We do that with CentOS as well as with RDO, as well as with the Puppet modules that we use to install and configure the different components. So for me, one of the very exciting exciting parts of our journey into OpenStack is actually to be able to contribute to these upstream open source projects. We used to have a rather inward-looking, not invented here syndrome. It was pretty strong at CERN. Now actually we contribute, we work a lot with other community members, which is actually lots of fun. It also means that I actually get to go and stand up here and talk to you about that. As I mentioned, we use at CERN we use Puppet for the config management. We contribute upstream to all these projects as much as we can. And we do updates. We do a lot of updates actually. The many different components that you saw on the previous slide, we upgrade typically one at a time. Most of the upgrades can be done rolling. The major exception to that one is Nova, for which we typically announce an API downtime of half a day while we upgrade the control plane and the hypervisors. But we've been upgrading relatively smoothly since 3 years. So that's going well for us. We test this using PackStack, an RDO tool, and DevStack, an OpenStack tool. And we do that in a development environment where we actually mimic the full CERN cloud environment. We can do that on a laptop. This is something that I still think is rather magical, because we know that the OpenStack environment is very well tested and very nicely contained, but the integration into the CERN environment, where we've got a very special network setup, like every organization, the network setup is odd, where we have to interact with account management, with Microsoft Active Directory, etc. To mimic all that, mock that up into a development environment, I think is, I'm still amazed that we can actually do that. But it does allow us to test every component and the upgrades as well, so that we don't get too many surprises on the days that we do our upgrades. So here you see how the CERN setup has evolved over time. Our first production service was in mid-2013, and we've been upgrading ever since. And you see that we've been adding more and more components to our service offering with time. This year we are adding OpenStack Magnum, and we are adding Neutron. The only thing, so we say, the only big component of OpenStack that we are not offering is OpenStack Swift. In fact, CERN, a thing that's missing from my presentation is actually how we deal with data access. I'm focusing on the compute part. Data access is still very much done with protocols and services that have been developed for high energy physics at CERN. So in that part of the department, if you like, the not invented here syndrome is still alive and kicking. So we do not offer Swift, but apart from that, we're offering an enormous amount of services, and ever more, because there's some interdependencies between them as well. So what is being done on our cloud? Well, a lot. This slide here shows the use cases that we are confronted with, because we're not just doing physics number crunching. The batch service is the main use case in terms of resources, but there's many more than that. We've taken away all the physical machines from our server-hugging colleagues, and they are now providing all the services on virtual machines, both in the department as well as in the experiments. Build machines are an example there, where we had to work quite closely with the experiments to make sure they also get some performance out of their virtual machines. We are running engineering services, we are running license services, we are running infrastructure services. Active Directory is being run there. The mail service is not yet, but I hope that one of these days we'll be able to do that as well. If you want to book a hostel room at CERN, it goes via a virtual machine that is on OpenStack. And as you can imagine, for such a wide range of applications, all users feel that their application is critical. And I'm not in a position to challenge that, huh? So what do we do there? For those server consolidation use cases, performance is usually not as important as durability. So we make sure that the hypervisors are configured to have some redundancy, typically in the disk layer. We set them up in a way that that virtual machine migration, preferably live migration, is an option, so we can move things around if the need arises. Persistent block storage is important for many of these, so that's where the Cinder service comes into place. And as I mentioned before, we tend to run our Linux VMs under KVM and our Windows VMs under Hyper-V, although we are now starting to move them from Hyper-V to KVM. As you can imagine, that's also an interesting exercise. And there's lots of them. In our 200,000 cores, about 30,000 cores are used for these use cases: server consolidation, development boxes, and personal VMs. It's actually quite a lot. So at the moment we're not doing a lot of virtual machine overcommit on the hypervisors, but we will. We used to run everything on hypervisors with spinning disks. So IO8 was a big problem, but now that we are progressively moving to SSD-based hypervisors, we can actually start to do some CPU overcommit and not be bothered with IO constraints. So that's going to be interesting to see how that works out in practice. Our other use case, where actually the most of the resources go, are the compute workloads. Now in these cases, we don't care for live migration at all. We don't care particularly for durability either. So we can optimize the hypervisor layout for compute efficiency, which means that on KVM hypervisors we configure CPU pass-through. And the flavors that we offer to our customers there are NUMA aware. To get the last, to minimize the virtualization overhead on the CPU as much as we can. But even there, we have very different workloads, and I mentioned 3 of them there. Our classic batch systems, which are LSF and Condor based, they are very long-lived virtual machines. They tend to be 18 or 16 core virtual machines, which is pretty big because our typical worker nodes these days have got 64 SMT cores. And for efficiency reasons, shall we say, very often we've been providing full node flavors. Full node I put into quotes here because all our the hypervisors that we used to buy, they were very different. Some had 24 cores, some 48, 64, 16. So it's very easy for a customer to say, I want a VM that spans the whole hypervisor. So what does that mean in practice? It means a lot of variety, and I'll say a bit more about that. We're doing the CMS Tier 0 farm. That's the reconstruction of the data that comes directly from the pit. Is also done on OpenStack VMs in the data center. These tend to be medium long-lived and 8-core VMs. It's a relatively straightforward use case. But the most exciting one and the different one is a product called vCycle, which is run by typically by the LHCb collaboration, where the VMs are extremely short-lived, about 10 minutes or so, and they typically tend to be single-core. So on the one hand, we have to provide infrastructure for 32 core VMs that will live for months, and on the other hand, our infrastructure should also be able to provision VMs that live for only 10 minutes and then get destroyed and recreated with a single core. And if you think about that, that has very big implications for the architecture that our service should have. In particular, the single core VMs, they all need an IP address. So that one hypervisor, and I already alluded to the fact that at CERN networking is also special, that the hypervisors, some of them will have only host one VM and others will host 64. We have to make sure that we can allocate all the resources to these different use cases there. So the good part here is this is very low SLA. If hypervisors die, they die, and the jobs get resubmitted. And this is where the bulk of our compute goes, and typically most of the hardware that we buy ends up running this sort of compute workloads. And this is our biggest problem: the very wide spectrum of hardware. We are very much a brownfield deployment. When we started to do OpenStack, we were like any deployment, we were given a few machines in a corner. And then we were given a few more machines and a few more, and now we've got 7,000. We tend to buy our hardware about twice a year. We buy the cheapest we can get, which basically means that we have 2, 3, 4 different kinds of hardware coming in every year. We run them for 4 or 5 years, which means that the hardware that is now 4 years old is completely different from what we have these days. And we want to offer a uniform service to our users. We don't want them to look under the hood. We don't want them to know that actually, well, you know, the machines have got different processors from those, and these have SSDs, and those are in 10 gig, and those are in Wigner, and those are in Budapest. They cannot handle that complexity. We have a hard time handling that. So this enormous variety is what makes our life interesting. And I'm very happy to say that we are going to cut hard into that spectrum and get rid of a lot of these old machines this year. So commodity hardware is great because it's cheap. On the other hand, since it's changing so often, it's actually very hard to run a sustainable infrastructure of this size on commodity hardware because it's very variable. So what we do offer to our users are different flavors or instant types. So typically our users will get to deploy VMs of up to 4 cores. Amazon style, they get to about 2 gigabytes of RAM per core, a bit less because we need something for the operating system as well. And our more important customers, they can get access to larger flavors of 16 or even up to 32 cores. And we can tailor them. We have a lot of private flavors in our back pocket, which we can give to very special use cases. And I can tell you, there's lots of special use cases. Storage. I mentioned we use Ceph as a backend. We actually also use NetApp as a backend. That's not particularly commodity, I can say. But if we want to offer volumes to machines that are running on Hyper-V hypervisor, Ceph is not an option. Ceph is not available for Hyper-V. So since we have some NetApp, we are providing NetApp volumes to VMs that are running Windows. And also we have a couple of, so we say, very demanding customers, the pension database, for example. As you can imagine, service managers there are extremely worried about reliability, and we put them on NetApp to make them feel more secure. Although in practice, the Ceph volumes are as secure as the NetApp ones. So we can play with a number of IOPS that we make available to different volume types. The location, we have different locations on critical power as well as on physics power. We have a special area in the computer center which is diesel backed up for more critical services. So this is roughly what we tell our users. You can use different volumes, you can use different flavors, and off you go. Build your VMs there. That's what we expose to them. A quick slide on service automation. With a small team with lots of hardware, we need to automate our services as much as we can. We use an open source tool called Rundeck, which is not an OpenStack tool, but I would like to plug it here anyway. Which we can automate our procedures and try to glue everything together. So we have to talk to OpenStack, we have to talk to Active Directory, we have to talk to our monitoring systems, we have to talk to our ticketing systems, and we use Rundeck workflows to take machines out of production, to inform the owners of virtual machines that a machine needs to be rebooted and stuff like that. It's been very good for us, and we heavily rely on that. This year is the first year that we actually get rid of hardware, and quite a bit as well. So we are decommissioning some 1,600 servers that we've been running since the beginning of times. So most of those machines, you wouldn't be surprised to hear, are running compute workloads, low SLAs, which is fine. So we just tell our users, look, you better delete these machines in the coming 2 weeks because we need to decommission the hardware. A smaller set are running service VMs. Unfortunately, there's many of those. We've got about 5,000 of these, so we say, pet VMs, where the users may be attached to them. So we'd like to migrate those VMs for them. And we've got quite a lot of experience now with virtual machine migrations under OpenStack. We started to do this while we were still running Nova Kilo, which had a which needed quite some love, if you want, for virtual machine migration. I'm happy to say that in the Liberty release that we're running now, things have improved quite a bit. So we're in the middle of a campaign of migrating 5,000 virtual machines. Live when possible, cold when necessary. We can only do live migration of VMs that do not have volumes attached. Or we can only do live migration of VMs between compatible CPU architectures. So we're actually getting rid of our AMD boxes now, but we have to do cold migration of the VMs that they are hosting to our Intel boxes in the coming months. We are making things more uniform. So it's a heavy campaign, but I'll be very happy when it's over because things will be much more uniform than they are right now. Another exciting migration we're doing is to go from Nova Network to Neutron. Now, those of you who have been operating OpenStack know that in the early days, networking component of Nova was integrated in Nova. It was called Nova Network. And since quite a while, that has been broken out into a project called First Quantum. And I changed name 3 or 4 times. I think there are people who can tell you the history of that. And Nova Network has been on the verge of deprecation for a very, very long time. So we've been dragging our heels there a little bit to wait for things to consolidate there. And it's clear that now we have to get out of Nova Network and move to Neutron. All new deployments are done with Neutron. We have to just get out. So during this year, we've actually put our first Nova cells with Neutron into production. Now we just have the little task of converting about 35 cells that still run Nova Network to run Neutron instead, which is going to be exciting as well. That's a 2017 project. I just talked about everything that's on this slide here. We for a very long time we had been waiting for a magical unicorn procedure to do a transparent migration from Nova Network to Neutron, and it never materialized. And then we realized, but wait a sec, all the other big deployments who are waiting for this, they're doing their own thing. I think we probably have to do our own thing as well. So we're doing that now. Another recent addition, I mentioned before, we are participating quite a lot into Magnum developments, so the container orchestration as a service of OpenStack. We are supporting Docker Swarm and Kubernetes, and since not very long, we also support Mesos as a backend, if you like, for Magnum. This is terribly exciting because many of our bleeding edge customers are very interested in containers, and they want everything and the moon, and we are happy to provide that. One of the cool things of I think of the CERN OpenStack infrastructure is that actually we've got partnerships with Rackspace who fund fellows to work on upstream developments. So we have a fellow who is contributing directly to OpenStack Magnum and make things work for us, which is very, very cool. For those of you who will go to Barcelona, make sure to check out those sessions where that work is being presented. Another fellow that worked for us and Rackspace has been working on Cloud Federation. So we are offering resources to members of the EduGain academic federation to our resources. We also worked on Keystone to Keystone Federation, but that's not something that we managed to put into production. But the idea here is that we can actually have OpenStack clouds talk to other OpenStack clouds, that you do not have to carry your credentials around in the way that Monty was showing, but actually you present yourself once and other clouds trust you through federation. Which is, so you can imagine, if, this is a bit of a pipe dream, but if all of our 300 institutes would be running OpenStack services and we have got a federation across, that would actually make the grid quite a bit more simple to operate. Oh wow! I have a few slides on CPU performance issues because this was a very big thing last year for us. I mentioned we had these full node VMs that we needed to provision, And we realized that actually that the CPU efficiency of these beasts was not very good. In other words, the virtualization overhead for these very large VMs on our KVM infrastructure was very poor. We were losing up to 15%. And we set out to understand where that went. And we found actually that we should start to use new malware flavors, which we are now doing everywhere in our compute cells. We played with transparent use pages, CPU pinning, and we managed to get those inefficiencies to an acceptable level, below 5%, as you can see there in the bottom. They're very interesting presentations on what exactly we tried and we did and what failed. That I encourage you to look online if you're interested in that. But now our virtualization overhead is in very acceptable ranges. Also, we're getting out of these famous full node VMs, and we're trying to steer our users to use 8 or 16 core VMs at maximum, where the CPU overhead is very acceptable. We did come across a very exciting bug once we deployed this NUMA aware scheduling, which meant that instead of being very efficient, after a while some machines became extremely inefficient. And it took us half a year to figure out what that was, and we decided to switch off EPT to much effect. And there's a link to a presentation on all that for you. I'll just skip that one. One slide on our future plans. So in addition to upgrading and operating and adding things, growing our service, we are looking at a new OpenStack project, new for us, that is to say, bare metal as a service, Project Ironic. We still have a few legitimate use cases for physical machine provisioning. And we would actually like to provision those to our users in an OpenStack way, using OpenStack APIs, so we can actually leverage the whole accounting infrastructure and the identity management, etc. So we do all our resource provisioning, virtual or physical, under the OpenStack umbrella. So we have somebody starting to look at integrating Ironic into our CERN environment in the coming half year. And as I mentioned before, we have started to see if we can replace Hyper-V by KVM. The initial results are very positive. But this is something that I think will keep us busy for the best part of 2017 as well, because we have a few hundred machines running Hyper-V. So in summary, at CERN we've been operating OpenStack for 3 years now. Our installation is huge. As I said, one of the cool things about running an OpenStack service there is actually the possibility to contribute back to the community. We are involved in Nova developments, specifically when it comes to the cells feature. We've got patches into Keystone identity management, in Magnum containers as a service, into Federation. We work with the RDO community. We have responsibility for certain RPMs, notably the EC2 API. In there is a certain contribution. The Puppet modules that we use, we contribute back to, and this is actually very cool. The service is very stable. I must say the OpenStack core is much more stable than I would have believed when I started a few years ago. We are part of the OpenStack operators community, where we share our experiences and playbooks with the other large deployments and other operators, which is fun again. It's not all plain sailing. There's a lot of hard work going on behind the scenes to actually run this as seamlessly as it seems. In particular, I talked about the replacement of hardware campaigns and the upcoming replacement of Nova Network by OpenStack Neutron. But hey, it's work, it's fun, it's good. And we maintain a blog, which I recommend you have a look at. There's a very interesting recent posting on a Kubernetes test where we run 2 million requests per second using OpenStack Magnum on our cloud infrastructure. And that's where we wrap up. So I hope that I've been able to show you that it actually works in production, even at our scale, with a relatively small team. It's a very cool community to be a part of, and it allows me to actually travel and come here and talk to you guys. So if you've got any operational or any other questions, now would be a very good time to ask them. Thank you.
Thank you, Jan. It was really interesting.
There's a question over there.
So you mentioned you have highly heterogeneous hardware per cell in your deployment. Is your hardware homogeneous per cell or not?
So the question is, the heterogeneous hardware that we have, is that at least homogeneous per cell? The answer is yes and no. Yes, it is for the more recent cells. The purchases that we do every year, we are buying several thousands of machines, and we carve those up into cells of 200, typically 200 machines, and there's uniformity in those cells. For the older deliveries, we never had that luxury. So we have some older cells where it's a complete mess, frankly. And those are the machines that I've been talking about at length that we are getting rid of right now. So we are aiming at having uniformity within those cells, but we're not there yet. Ask me again in a year from now. Things should be much better.
How do you monitor this?
How do we monitor this? We monitor this with I'm afraid to say, with a homegrown solution, by and large. We have an in-house monitoring project that we developed over 10 years ago. I'm guilty for that one as well, actually, which we've not been able to get rid of. We don't use any. We don't use much in terms of OpenStack delivered monitoring. We do a lot of stuff ourselves. Not much you can learn from that, I'm afraid. Yes?
In the beginning, you mentioned a little bit about the impression figures of what a detector actually computes or generates in data. But you mentioned in your presentation about the non-persistent storage connected to the virtual instances and cells. But what about the persistent data? How do you keep that on track with the expansion of the OpenStack cloud and keep that as a kind of a predictable and usable solution that achieves the same performance in a scale that you are using the OpenStack cloud?
So how do we make sure that we can scale our compute part and our data, persistent physics data part, in a way that we can actually operate this? It's a very interesting question, because these are two different worlds, and we basically we're not really relying very much on software there. We're mainly relying on planning. We know the predicted data rates. We know how much money we'll be getting, so we negotiate with the experiments how much data we can actually handle for them, and then we know how much tape we need to buy for that, how much disk space as a cache they need to buy, and how much compute. These things are done separately. So I'm afraid there's a big disconnect there, and these are different systems as well. At the moment, we are running the compute on our hypervisors, and the data is stored on a completely different set of hardware.
Give me a call when you converge.
Okay, the last question.
Don't hold your breath.
Hello. Yes.
Hi.
I was just wondering about your neutron migration and what backend you will be using.
Okay. Now you find me out. You find me out. I'm an imposter. I'm afraid I can't really answer that for you. We can have a chat offline for that. But,
Okay. Thank you, Jan.
Linux Bridge, by the way. That's what we started.
Okay. Thank you.
Thank you.